Hello, honors physics. So this is my basement actually, and because it seems like we might be in this for the long haul, we worked really hard. I will give you a tour when my kids pick it up, so maybe tomorrow, all weekend to kind of clear out the unfinished basement and build a classroom. So this is the whiteboard. So I'm gonna try doing lectures via webcam. And then that way when we're live during our class time, we can just kind of interface with each other and ask questions, and it takes a little bit of the pressure off of all the technology working at that moment and fitting everything in, etc. So we'll see how this works, see what you think of it, see what I think of it. Sorry, I look like a bit of a hot mess. It is currently 7:45 p.m. and it's been a long day. So, I miss you a lot. This is strange, but I'll just kind of dive into things and we'll see how it goes. So, we're going to start with uniform circular motion. We already talked about that just a little bit. We didn't take notes on it yet last week. So, I was calling uniform circular motion UCM. And I had you do a lab it feels like years ago, but just like a week and a half ago, where you were taking some data, and I'm going to ask that you graph it when I write the assignment. I'll ask that you graph your data before you watch this. So you should have data, and you might have made your graphs a little bit differently, but you had data where you were looking at how changing the force affected the velocity. So that's when, this is the graph where you're swinging, or the lab where you're swinging the thing over your head. And so when you were changing the masses that were hanging while you were swinging, that's when you were changing the force. That was producing more tension in the string. You then should have held that constant, and you were looking at how changing the radius changed the velocity. So some of you got all the way up to, I remember seeing you like 1 meter, or some of you not quite there, but then you had 5 different radii that you did, and you looked at how that impacted the velocity. And then the final thing that you looked at was the mass. So that's when you were changing the rubber stopper. And so you saw, what happened when you had smaller masses versus a larger mass, and how that might have changed the velocity. So we're going to kind of talk about what those graphs shoulda, coulda looked like when I introduce the equations in a minute. In uniform circular motion, just as a reminder, this is a motion where as you were swinging around your head for each trial, right, you changed it up between trials, but as you were swinging around your head for each trial, you would have had a constant radius and a constant speed. And we said when something is in circular motion, it's still accelerating because its direction is changing all of the time. So that acceleration, I'm kind of follow your PowerPoint. So I'm going through just to make sure that I stay in order. Sorry, big face of me. Oh heavens. There we go. The acceleration when something is in uniform circular motion, it's called centripetal. I don't think I wrote that word up on the board last week. Centripetal acceleration, which means center seeking. So when something is rotating, again, we are right now, so things can be spinning in all kinds of different ways, vertically, horizontally. Like this is my name tag. I miss using it. This is what I mean by vertical. If I swing it over my head, that's a oh, you can't see it. There it is. That's a horizontal circle. You could have it at an angle or whatever. When it is spinning, whether it's spinning in a uniform way or not, even if it's just curving, it has this thing that I call centripetal acceleration. So this is non-uniform right now because I'm changing the radius as I go, right? But if I spin this in a uniform way, constant radius, constant speed, etc. In both of those cases, I have what we call centripetal acceleration. So centripetal acceleration means that it is towards the center. It's a center-seeking acceleration, which means that the net force is towards the center, right? Because F equals ma, so net force has to be in the same direction as acceleration. So in this case, the net force is caused by my name tag string, and it's always being pulled by my hand, my wrist, which is in the center of the circle, right? So we have a force towards the center of the circle. That is centripetal acceleration. Now, I don't have a whole lot of room on my crazy board, nor time. These videos take forever to upload. So if you're super bored in your quarantine, there's a derivation of its geometry. It has like arc length and all kinds of stuff in your textbook, or you can take my word for it. And the centripetal acceleration, I'm going to call it A sub C, is equal to V squared over R. So that is an important equation. We're going to have just a couple of important equations, so I'll bracket them on the board. Hopefully you can see it's a little bit of a glare. So A is equal to V squared over R. So to find it, you take the velocity, which for us is going to be constant for now, and square it, so direction doesn't matter. You divide it by the radius of your circle. So it's going to be a really, really simple thing. And again, this acceleration, always, 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 without exception, is directed towards the center of the circle. Okay. Two other important equations. One, or actually both you sort of saw in the lab, and so we'll come back to this lab. One is that if something is spinning in uniform circular motion, its velocity, to find that velocity, would be equal to circumference divided by time. Now, time here I'm writing as capital T. The word we use there is period, and that just means the time it takes for one complete revolution to occur. So in the lab that you did, again, just feels so long ago, but the lab that you did last week before exams, you should have found the velocity of your spinning rubber stopper using this equation. So you've seen that one. So T is the time it takes for one complete cycle to occur. The capital T just means period, so that we use that in circular motion, and eventually we would use it for waves. And then the final equation that's kind of important is if we put these two together, right? So Newton says, this is the equation we've been using a lot, sum of all forces is equal to mass times acceleration. If something is in uniform circular motion, so it's spinning at a constant rate, so the only acceleration is towards the center, that's it. It's not speeding up as it spins, it's not slowing down as it spins, it's keeping that uniform rate. Then we can say the sum of all forces is equal to MA, which would be mv squared over r. So I'm just plugging in what A is. So this is the third. So these three equations that I have in brackets, those are our three important equations for uniform circular motion. Now, this is the one that we really focused on in that lab. So I'm going to kind of come over here and talk about what those relationships should have looked like. Let's see if I can like shift this slightly. I don't know. So if we come back to that equation, the sum of all forces is equal to mv squared over r. The first thing you did in the lab, you looked at force versus velocity. So if we look at that in the equation, you held the mass constant and you held the radius constant when you did that lab. So what we see is force and velocity, they're directly related. Now this v is a v squared, so it wouldn't have been a straight line when you graphed it, but you should have seen some kind of a direct relationship. So if this was perfectly, like perfect data, this graph should have been direct relationship, but not linear. Like it should have looked like a little bit of a curve, maybe something like that. The second thing you were looking at was radius versus velocity. So I think I always think it's helpful when you're looking for relationships, put the two variables you're comparing on opposite sides of the equal sign. I don't know if you talk about that in math class or not. So if I rearrange this equation, it would be R times net force is equal to mv squared. So when you did this part of the lab, you had held the mass constant and the force constant. So you're comparing R and v squared. So R was directly related to v squared. So again, it should have had the exact same looking graph that F did. So bigger R's meant bigger V's, and here bigger F's meant bigger V's. And then the last thing you were comparing was the mass. So that was when you were changing the mass of the rubber stopper. Again, so this is kind of our first set of data. Here's our second set of data. The third set of data, if we put, I'm looking up at the top equation, if I put m and v on opposite sides of the equal sign, I have F over m is equal to v squared over r. Again, F and r were constant for this. If you look at this, this was an inverse relationship. It was also not linear. So something like this. So we would have seen as the m got bigger, the v got smaller, or vice versa. So hopefully your data supported that, but this is the equation that you were after. Now, again, it's been so long in my world, like everything has changed since you've done this lab. I don't know how sharp those memories are, but conceptually what's important are that these three equations, so the three that I have in brackets, are going to be the equations we use to solve the problems for this first part with uniform circular motion. So I'll do that as a second video just for upload time. Just work through some problems with these equations, but I did want to show you how that linked to the lab, and if you did the lab correctly, what you should have seen with your data. Now there's a lot of room for error with that lab. Remember, like it was hard to keep the string from popping up and down. Some of you were struggling with when it was swinging around that it would drop out at an angle, and that changed the tension. So you might have seen different errors in your data, and you might have had issue with what I'm saying here. But if done correctly, this was the trend you should have seen. Okay, bye for now. We'll do a second video in a second.